Let's take a look at one that involves the use of the chain rule. So let's look at the first partial with respect to x here. I don't know what happened there. My pen got out of control, but this is f of xy equaling this function. So let's rewrite this function as x times the quantity of 1 plus y squared, and then the radical of this whole thing would just be to the 1/2. Okay, so now we know that our function is this in exponential form. Let's go ahead and figure out the first partial with respect to x. So here again, everything that's not x is going to be looked at as a constant. All right, so I'm actually going to use the product rule, and then within the product rule, I may have to use the chain rule. So let's first start by using the product rule. So that's going to be the second, which is this. There's my second. Okay, times the derivative of the first, which is the derivative of x, which is 1. Okay, it's with respect to x, so we are deriving this. Derivative of x is 1, and then plus the first times the derivative of the second. Oh, the derivative of the second. That's this entire thing, and we're considering y to be a constant. Okay, we're holding y as a constant, which means the derivative of this entire thing is just 0. So your answer here, the first partial with respect to x, if you wanted to put it back in radical form, would be the square root of 1 plus y squared. Okay, let's look at the first partial with respect to y. So with respect to y now, we're holding x as a constant. All right, let's go through our product rule again. The second, 1 plus y squared to the 1/2. Times the derivative of the first. Oh, now our first is considered to be a constant, again, because we're differentiating with just respect to y. This first partial with respect to y. So the derivative of our first here, it's considered to be a constant, is just 0. All right, which means this whole thing is gone now. Okay, so let's move on here. Plus what? The first x times the derivative of the second. Well, we are able to differentiate this now because this is considered to be a variable, y, because it's the first partial with respect to y. So, all right, let's come up with the derivative of this then. Using the chain rule, okay? So that's going to be 1/2 times what? The inside, and then 1/2 minus 1 is negative 1/2. Do you remember the chain rule? And then times the derivative of the inside, which is 2y. So in this one, if you wanted to, you could look at it as what? Well, again, these are both gone. Let's go ahead and see if we can simplify this. This is correct, but if you wanted to simplify it, you could look at it as what? Well, 1/2 times 2, those are both gone. Then you have x times y. And so I'm noticing xy now is the only thing in the numerator. Why? Because you have a negative exponent that this quantity is being raised to. So a negative 1/2 means that this 1 plus y squared is really underneath the radical in the denominator. Okay, in this next example, we want to be able to evaluate the first partial derivatives of this function at this given point, -5, -4. So there are different ways to notate this, but how I'm going to present it is basically the same way we've been doing it. So in other words, first find the first partial with respect to x. We'll do that one first. So with respect to x, this first term, notice, does not contain a y. You just come up with the derivative of this like you would have back in chapter 9. So the derivative of this would be bring a 3 in front. 3 times 4 is 12. Take 1 away from that, and you get 12x squared. This one, keep in mind, we are differentiating with first partial with just respect to x. That means because there is now a product involved here with the x and the y, you're going to leave y cubed. You're going to leave this as if it were a constant. Okay, so you're only differentiating then this x. The derivative of x is just 1. So you end up with 5y cubed. Again, you're holding this as a constant. So the 5y cubed, that stays the same. The derivative of x is 1. You're left with that. Okay, now what we want to do is we want to actually determine what the value would be of this first partial with respect to x at this point. So we would now write this, and it would be equal to, well, whatever you would get here if you replace the x with the -5, and if you replace the y with a -4. So if you run that through your calculator, you should end up with, I believe, -20. So this is, if you looked at the surface of his 3D model, this actually is representative of the slope with respect to the x-plane at this point in space. But if you can come up with -20, you're in good shape. All right, the next one then would be the first partial with respect to y. So this is all now considered to be a constant because, again, you're just differentiating with respect to y. So this now, the derivative of this is 0. It's gone. Okay, moving to the second term. The x is considered to be, again, a constant, so you get 5x. And we're leaving it here, again, for this particular term because there is a product occurring between x and y. So you have to always leave the x if there's a product occurring. All right, so with that being said, what's the derivative of y cubed? The derivative of y cubed, of course, is, with respect to y, is 3y squared. So in this particular one, you get 15xy squared. Okay, so here again, if we wanted to determine the first partial with respect to y at this point in space, we would just use substitution now. So we'd get 15 times what? The x value, -5, the y value, -4, and then we square it. And I believe if you do this one correctly, you end up with -1,200. And this would actually be representative of the slope with respect to the y-plane at this point in space on our 3D model.